Let's dive right in. Today, we're exploring a fundamental, kind of mind-blowing truth in chemistry. A molecule's identity is so much more than just a list of its parts. We're going to see how the specific three-dimensional arrangement of atoms, its architecture, is what defines, well, everything about it. So let me start by asking you a question. Can two things built from the exact same components be completely different? I mean, sure, you can take a pile of wood and nails and build a chair or a table. But in the molecular world, this idea goes way deeper, and the answer is a huge, emphatic yes. And believe me, the consequences are profound. Okay, check this out. On the left, we've got ethanol. Yep, the alcohol in drinks. It's a liquid at room temperature. On the right, dimethyl ether, an industrial propellant, basically something you'd find in a spray can. It's a gas that boils at a freezing negative 24 degrees Celsius. I mean, totally different things, right? But here's the crazy part. They have the exact same chemical formula. 2 carbons, 6 hydrogens, 1 oxygen. So what gives? It's all about the architecture. To solve this little mystery, we have to start at the first level of molecular design, the blueprint. This is all about how the atoms are connected to each other. And in chemistry, we have a name for these variations. We call them constitutional isomers. So, a constitutional isomer has the same parts list, the molecular formula, but a completely different set of instructions for how to put it together. Think of it like having this same set of Lego bricks, but building a car instead of a house because you connected them in a different order. Simple as that. Let's start with a really simple example, butane. With just a handful of atoms, it turns out there are exactly 2 ways you can build this thing. The formula for butane is C4H10. With just these 14 atoms, there are only 2 ways you can snap them together. You can make what we call N-butane, where all 4 carbons are just lined up in a row. Or you can make isobutane, where one of those carbons branches off from the middle. Same parts, totally different blueprints, and because of that, they have different properties. Now, here is where it gets absolutely wild. If we just bump that up to 10 carbon atoms, the formula for decane, the number of possible blueprints or isomers just explodes. It goes from 2 to 75. This is why chemistry is so incredibly rich with possibilities. It's the reason we have this vast library of molecules for things like new medicines, all built from the same few basic atoms. Okay, so beyond the basic carbon skeleton, there's another layer to this whole architecture thing, special attachments we call functional groups. The best way to think of these is like specialized modules or apps you can plug into the main structure. They're what give a molecule its personality, its characteristic behavior. A super common one you've probably heard of is the alcohol group, an oxygen bonded to a hydrogen, or OH. Anytime you see this little guy attached to a carbon chain, you know you're dealing with an alcohol. That ol at the end of ethanol, yep, that's this guy right here. Next up, the ketone. Its key feature is a carbon atom that's double bonded to an oxygen. We call that a carbonyl group. This little feature is incredibly important in biology and industry, and it gives molecules the own suffix in their names. And finally, for our quick tour, we have the carboxylic acid group, or negative COOH. It's kind of like a carbonyl and an alcohol group sharing the same carbon. And as you can probably guess from the name, this is the functional group that makes things acidic. It's literally what puts the acid in acetic acid, which is, just vinegar. But hang on, what if the blueprint is identical? What if the atoms are connected in the exact same order, with the same functional groups? Well, now we have to go 3D. There's an even more subtle layer of architecture, the molecule's actual 3-dimensional shape. And this, my friends, is where things get truly mind-bending. The key idea here is something called chirality, which is really just a fancy science word for handedness. Seriously, look at your own hands right now. They're perfect mirror images of each other, right? But no matter how you turn them, you can't lay one perfectly on top of the other. A left-handed glove just won't fit on a right hand. Well, it turns out that tons of molecules have this exact same property. So these non-superimposable mirror image molecules, we call them enantiomers. And this special property pops up whenever a central carbon atom is bonded to 4 totally different groups or atoms. That one little structural feature is enough to create both a left-handed and a right-handed version of the molecule. Now, you've probably seen these weird R and S letters in front of chemical names and thought, what is that? Don't worry about it. Seriously, it is just a label. It's a universal system chemists use to keep things straight, to say, okay, I'm talking about the right-handed R version or the left-handed S version. That's all it is. Okay, so who cares, right? Does this handedness actually matter in the real world? Oh, you have no idea. It's absolutely critical. Think of it like a key fitting into a lock. The enzymes in our cells, the machinery of our bodies, they are the locks. And they are incredibly picky. For the amino acid alanine, our body uses the natural version as a building block for life. It's the right key. But its perfect mirror image, the unnatural version, is the wrong key. It just won't fit. Our body can tell the difference, even if they look identical on paper. All right, so we've established that how atoms are connected and their 3D shape are both crucial. But let's get to the core question, why? Why does this architecture have such a powerful influence on what a molecule actually does? The answer really comes down to stability, especially in the chaos of a chemical reaction. See, when molecules react, they don't just magically transform. They often pass through these really unstable, high-energy, fleeting states called reactive intermediates. You might get a carbocation, which has a positive charge, a carbanion with a negative charge, or a free radical, which has a lonely, unpaired electron. The stability of these little guys determines which reaction pathway is easiest for the molecule to follow. And this is where structure has a direct, massive impact. For a carbocation, with its positive charge, it's happiest, most stable, when the charged carbon is connected to 3 other carbon groups. Those neighbors help spread out and stabilize that charge. But now, get this, for a carbanion, which is negatively charged, the exact opposite is true. It's most stable when it has fewer carbon neighbors getting in the way. This shows you, right there, how the local architecture literally dictates which path a reaction is going to take, which in turn determines what product you're going to make. We've covered a ton of ground here. Blueprints, building blocks, 3D puzzles, all of it. So what's the big picture? What's the one thing you should really take away from all of this? It's this, a molecule's formula. That's just the shopping list. Its architecture is the recipe. And it's the recipe that determines everything. From designing a life-saving drug that fits like a perfect key into a viral enzyme, to creating a new material strong enough for space travel, understanding that 3D structure isn't just some academic exercise. It's the blueprint for the future. And it all starts with asking one simple question. How are the atoms put together?